again, let me remind you what we've done so far. We started this semester with laying down the foundation of the world of electricity, right? So we learned how to find the electric field and the electric force. Again, as I told you already several times, once you know how to do that, you lay down the foundation. Then the rest is just applications, right? But we looked at that foundation, and we saw that electric force is a conservative force, and as a result we managed to build an alternative approach which allowed us to simplify calculations. So we built the energy approach, which can be used to solve problems, right? And after that we decided to apply all that for a particular situation, for a particular type of problem. So we went to describe simple circuits, and we spent like a week and a half describing simple circuits. Okay, after that, what? Again, we lay down the foundation. The rest is just application of that foundation to describe that particular situation, or this particular situation, or that phenomena, right? We already spent some time describing circuits, one of the one of the applications. So pretty much at this point, we can say, what else do we want to know about the electricity? Of course, you can come up with the new phenomena, right? And we can try to explain that. But I think it's enough. I think it's time to say a sort of goodbye to the electricity. That's why I put this picture, right? Bye-bye electricity won't be missed, right? And it's time to move into the new world, to start introducing something new, right? So it's time to move to the world of magnetism. For now, it sounds like, okay, over there is a world of electricity, right? And over here, there is a world of magnetism. And between them, there is a big wall, the border, right? But the actual situation about their independence or separation of these two worlds, world of electricity and world of magnetism, we will discuss that maybe in I don't know, 5-6 classes, right? In a few classes, right? And we will see how independent these two worlds are, right? Or how connected those two worlds are. But for now, it's too early to dive into that discussion. So for now, let's move into the new world of magnetism. And the introduction of this world of magnetism will be very similar to the introduction of the world of electricity, right? Again, we need to introduce some conventions, right? So then we will have to lay down the foundation. And again, what is the foundation? Once you know how to find fields and forces, you are the king. You know everything about that world. So very similar we're going to do in this world of magnetism. But before we start actually introducing, let's look at one phenomena which indicates that something is missing, that something new must be introduced, right? So let's look at this. Oh, first of all, I need to bring my slides forward. Yeah. So let's look at, it's chapter 29. Let's look at this. Every time I want to say like a simulation, but it's not a simulation. No, it's just a cartoon, a simple cartoon, right? This. Oi. Okay, so what do we have here? We have two pairs of electrons. First pair over here, you see this blue and green. Originally, they are stationary. So pretty much they don't move. And we hold them. And then we're going to release them. And of course, they're going to interact. Since they're both negative, right? Negative charges, of course, they're going to repel themselves. And we will look at the results, outcome of them repelling each other. Then next pair of electrons, of course, identical, right? Will be these two, again, blue and green, but now they're going to move with velocity v0. Both of them will move in that direction. And also, since they're, again, both negatively charged, of course, they're going to exert electric force on each other. And of course, they're going to push themselves away, right, from each other. And we're going to look at the outcome of this motion, right? So let's look first at two stationary electrons. Again, right now we know only about the electric force. And based on that knowledge, let's see at the outcomes of these two these two motions, right? So let's look first at these two stationary electrons. Oops, again, pressed on the wrong place. So you see, they moved. All right, so they repel each other, of course, and that's the outcome, right, of their interaction. Now let's look at the result of the interactions of these two electrons. Now they move. So damn it, sorry. So the first one and now the second. I need to press on the. So you see, it's a completely unexpected, right? So now these are moving electrons. They push themselves apart, but the distance between them is smaller than the distance between the electrons which were stationary. How come? Because based on the knowledge which we based on the facts laws which we learn for in the world of electricity, the outcome must be the same, because there is only electric force acting between these two pairs of charges, right? According to the laws of electricity, right? But the distances between these charges are different. How come? So it's a clear indication that something is fishy. It means that we're not including something in this in our description. Something is still not included. We still have time. So, so that's what people observed. Let's say, I don't know, 250 years ago, right, or maybe 300 years ago, when again this was hot subject. So now they needed to somehow explain the differences between those two electrons and these two electrons. And back then, there were two suggestions to make two different approaches. The first approach, some researchers thought, you know what, we have this electric field, electric force, let's just modify that somehow for moving charges, because obviously something is fishy with moving charges, right? And so they were suggesting to somehow just modify electric force and electric field for the moving charges. But there was an alternative approach. Some people suggested, you know what, let's introduce the new field and the new force. Because again, guys, you need to understand that what we do in physics and science, right, we just model the nature. It doesn't mean that God created the world using these laws which we're writing down. No, I don't know what was and how God created this world, right? But somehow it was created and we live in this world, and we're just trying to describe it using our ideas, using our formulas and so on and so forth. It's just our way of modeling. I'm sure it's not the only one, it's not the only way to model this world, right? So back then, so there were two alternative sort of suggestions to take two alternative approaches. First, just to modify electric force and field. The second, just to introduce the new field and new force. So the second approach won, and people decided to introduce the new field, magnetic field, and the new force, magnetic force. And as a result, so when these electrons move, there is also magnetic force, because they move, there is also magnetic force acting between them. And that force is force of attraction, right? So as a result, as they move, electric force tries to repel them, but the magnetic force tries to attract them, right? Bring them closer to each other. As a result, the net displacement you see smaller than the net displacement for stationary electrons, since stationary electrons did not experience this magnetic force, which we haven't introduced yet, right? So now it's time to introduce this new magnetic world, and this is just a I don't know, evidence example where people could see the first signs that something new must be introduced, and they decided to introduce this new world of magnetism. Okay, so now let's introduce it. And okay, so in the world of electricity, of course, I will compare quite often, right? These two worlds, whenever you have a charge, okay, point charge, and that point charge all the time produces electric field. It doesn't matter if that charge is stationary or if that charge moves. In both cases, it will produce exactly the same electric field. That's what we had in the world of electricity. Now, in the world of magnetism, for a charge to produce magnetic field, it must move. Only a moving charge can produce a magnetic field, and that's why in that evidence, in that sort of cartoon which I showed you a few minutes ago, we saw that additional effect only when charges moved, because only in that situation magnetic field can appear, and of course magnetic force. So now you need to remember, only a moving charge can produce magnetic field. And you know what? You will see in a few classes that everything in the world of magnetism is in dynamics. So for a charge, for a charge to produce magnetic field, it must move. And then in a few classes we will see so that for a charge to experience magnetic force, again it will have to move. If charge is stationary, it's not going to experience magnetic force. So you see, every time, everything in the world of magnetism must move in order to observe something, right? So first, in order to produce magnetic field, a charge must move. So as a result of this basic fact, we can come up with three typical systems which can which will produce magnetic fields. The first, of course, the first system is just a point charge which moves, okay, must move, and then of course there will be magnetic field. We're going to use symbol B to denote these magnetic fields. Right. So moving charge produces magnetic field. Then what about if you have bunch of identical charges, or for example bunch of identical electrons drifting in the same direction? Of course, that is a current, electric current. And since each of those electrons are going to produce its own magnetic field, of course, there will be sort of like a net magnetic field produced by a current. So the second system, any current, a wire with the current, right, of course, is going to produce also magnetic field. So that's the second system. And the last system, the third one, is a permanent magnet. Is a permanent magnet. That's the last system which is going to produce magnetic field. But of course, logical question, reasonable question. So as I told you, every time there must be a moving charge or moving charges in order to produce magnetic field. Where are the moving charges in a permanent magnet? Right here we have here charge moves. Here a bunch of charges, they move, they travel again, they produce magnetic field. Now in a permanent magnet, what is moving, right? Why is there magnetic field around permanent magnet? Some of you might realize, right? So what's the story? You remember classical model of an atom? There it is. right? So what we have? We have at the center we have nuclei, of course, which don't move, which doesn't move. But what about electrons? Electrons orbit around that nucleus, right? Orbiting, what does it mean? It means they're moving. They're circling around that nucleus, right? Circling, orbiting, it means they're moving, right? So it means that, of course, they also going to produce magnetic field, right? But of course, there must be some additional requirements met, right? Because not every material gives us a non-zero net magnetic field, right? So there's only special type of materials can generate magnetic field. But we're not going to discuss that. But anyway, so you see what now you understand which moving charges produces this magnetic field which we observe around permanent magnet. Now we can play with these three systems, right? Producing magnetic field. But you know what? We're going to use magnetic field produced by a permanent magnet to introduce some basic ideas, right, at the very beginning. Then we're going to use most of the time magnetic field produced by currents. That will be sort of like our workhorse. Yeah. Then for several years we used some expressions, right, which can be used to calculate magnetic field produced by the charge. But you know what? Our theoreticians, especially in the department, they were really against the fact that this book uses formulas to calculate magnetic field produced by a point charge, which are not kind of absolutely correct. The process of producing magnetic field by a point charge is significantly more complicated. So as a result, sort of we agreed that probably we'll just drop that part, that description of magnetic field produced by point charges shown in the book, right? So as a result, we usually use most of the time a magnetic field produced by a current, right? And for conceptual analysis, magnetic field produced by a permanent magnet. Right? Okay, so now let's use permanent magnets in order first to discuss some simple observations, then simple facts, and then some basic ideas and conventions. So first of all, of course, we all know, we all play with magnets. Our fridge is full of magnets, right? So you know that like poles repel. So I have two magnets, right? So I took them from the department. So I'm trying to bring them, and of course they repel. Of course, if I try, okay, I can, but it's difficult, right? So we all play, you know what I'm talking about. So like poles repel. Then it's just an observation. Right? And of course, unlike opposite poles attract, of course, if I flip this, of course, it's very simple, right? So because they attract, right? So this is just observations which must be stated, right? And so now what's next? Just now I talked about poles, but I haven't really introduced them, right? And we will introduce actually what does it mean North Pole and what does it mean South Pole and why we call that one North and this one South, right? But next logical sort of step, if somebody gives you a permanent magnet and tells you, right, so this is the North Pole, this is the South Pole, right? And after playing and seeing these simple observations, what would be your next desire? Most likely you would think something like that, right? So if there's a North and South Pole, so what if I just break it into two pieces? So, of course, you will expect that you will get separately North Pole and South Pole, right? But, okay, again, I'm assuming that you don't know anything, right? So you're like a child playing with a new toy, right? So, of course, any child would expect that you will get separately North and South Pole. But, of course, that child will be disappointed that if you break the magnet into two, you will get two smaller but full magnets. you'll have, you see, south, north, south, north. So you'll have two full magnets. Or maybe just a bad luck, right? So I didn't crack it in the proper direction or something. Okay, let's crack it one more time. Still, you will end up now with four, but full magnets, smaller four magnets. Again, south, north, south, north, south, north, and so on, right? It doesn't matter how many times you're going to break this magnet, every time you're going to end up with a full magnet. So now we can sort of state that there are no magnetic monopoles. No magnetic monopoles. Okay, it doesn't mean that it's impossible for them to exist in the universe. No one has ever proved. No one has ever proved that it's impossible for them to exist. Proved theoretically that it's impossible for them to exist. Right? It just means that no one has ever seen them. So far in our history of mankind, no one has ever observed the presence of any single magnetic monopoles. So as a result, of course, all equations in physics are written keeping that in mind, right? So all equations are written with the fact that magnetic monopoles do not exist, right? Let me ask you, what about electric monopoles? Did we have electric monopoles in the world of electricity? Yes, we did. We had them. What is basically a positive point charge? It's the positive electric monopole. What is, for example, electron? Negative point charge. It's a negative electric monopoles. So you see, we do have electric monopoles, but we don't have magnetic monopoles. So unfair, right? I don't know why. Right? It looks like God forgot to create magnetic monopoles. Maybe he was in a rush creating the world in 7 days, right? And he forgot to create magnetic monopoles. Maybe he was on a grant from NSF, right? I can easily imagine, right? So NSF panel got together, right, and discussing. Oh, look, what interesting proposal, right? To create the world in 7 days. So let's give him a grant, right? So he will create the world, and we will build our headquarters on the Earth, right? Right. Well, maybe in a rush he forgot to create magnetic monopoles. So, for whatever reasons, there are so far no one has observed magnetic monopoles, but electric monopoles, yeah, plenty. And as I told you, it doesn't mean for them. It doesn't mean that it's impossible for them to exist. And still, there are some research groups which try to find these magnetic monopoles. And if you watched that famous sitcom, The Big Bang Theory, right? You remember in one of the episodes, Sheldon Cooper got the NSF grant to go to the South Pole and he was trying to find magnetic monopoles, right? Right. And you remember what was the result? Because he was so annoying, right? That his friends just faked data for him, right? And he was. You remember how happy he was because of finding magnetic monopole. It's a Nobel Prize, no questions. Next year, immediately, the next Nobel Prize will be yours, right? And he was happy because he knew he would get a Nobel Prize. And then, of course, remember how crushed he was when he was told that all that data is just a piece of junk, right? It means nothing, right? So he quit the job and went to his hometown, right, somewhere in Texas, right? Yeah, so it's a big deal. I'm just making a point. So finding magnetic monopole would be a big deal. But so far, no one has observed, and all the equations are written assuming that there are no magnetic monopoles. Right. Okay, so now we need to introduce some conventions, some basic ideas. Basically, we're just trying to create an alphabet of the world of magnetism, right? Some simple facts, simple ideas, simple conventions, right? So that we can be comfortable and so we can play freely in this new world. And so a new convention, right? Again, yeah, from time to time we'll have to come up with conventions. So which convention I will tell you? But for now, so now we can say, yeah, we sort of agrees that magnetic field exists, right? And of course, the next thing, so how can we detect it, measure, probe this magnetic field, right? So basically, the question is, which object can be used to probe or measure the magnetic field? So again, the question is about a probe system. You remember we were facing this problem in the world of electricity, and we decided to use what? A small positive probe charge. So that was our probe system. So now we have to come up with something similar in this world. And of course, that probe system must first respond on the presence of the magnetic field. Second, it must be reasonably simple. And the last, it must be small so that we would not disturb the system which creates this magnetic field, right? So what can that be? What about small permanent magnet? It responds on the presence of the magnetic field. It's small, right? And so what else do you want? It's simple. What is simpler? Because there are no magnetic monopoles, right? So it must be some permanent magnet, right? So let's use that. And what do we usually sort of where do we usually see a small permanent magnet? Any device? Can you recall? It's a compass. What about compass? In a compass, we have that compass needle, which is effectively what? It's just a permanent magnet. Small, light, right? Simple. And usually, most of people, especially in old days, they had compasses, right? Why not? So that will be used as a probe system, right? Probe system. Now, next question, of course. The compass needle we know has the north pole, north side, and south pole, south side. So, which pole should be called north and which pole should be called south of the compass needle? So now we've come to the point where we have to introduce this new convention. So now it's a point for the new convention, and then based on that convention, we're going to label all the poles in the world, right? So, and in order to introduce this convention, let's bring the Earth into this game, right? We all know that the Earth has its own magnetic field. And of course, if you ask what's the reason for the presence of that magnetic field, most likely it's inside of the Earth, of course, you know, there is a molten iron core, right? Some liquidy stuff, of course, full of charges. And of course, that liquidy stuff, of course, it has most likely has inside some currents, gigantic currents, like Gulf Stream in the ocean. Of course, there is something like that in that iron core, right? And of course, it means that there is a motion of charges, right? And I guess that's the reason why we have magnetic field. Again, whenever you have motion of charges, there must be magnetic field around that. Magnetic field around that, right? So that's basically our explanations why the Earth has a magnetic field. Basically, it behaves like a permanent magnet because of the molten iron core. Right. Okay, so now let's just introduce a few simple facts which we all know about the Earth. Of course, it spins around this axis. So this is the axis of rotation. Of course, that side, this we called the north geographical pole, right? So this is our north geographical pole. And I emphasize geographical. Then, of course, the opposite side, it's the south geographical pole, right? South geographical pole. And now, so how did we use in the past compasses in our life? Every time we use compasses to find what? To find the direction to the North Pole, to find Santa, right? So every time we used pretty much for thousands and thousands of years, we used compass to find direction to the North Pole. So of course, as a result, how should you call that side of the compass needle which points all the time to the North Pole or North geographical pole. So this convention actually is not related to the physics, it's related to our everyday life, the way we use compasses. Since every time we use compasses to find direction to the North Pole, it makes sense from our everyday life point of view to call that side of the compass needle which points to the North geographical pole, to call that side as the North Pole of the compass needle. So this convention is barely related to physics. It's just more because we use it, we called this side as north side, okay, that side, red side, as north side because it's convenient from our everyday life. So again, that side which points to the North geographical pole, we're going to call as the North magnetic pole of the compass needle. So this is the convention. Now, once we sort of agreed to call that pole like that, then of course we can call the rest of the poles following the logic. So of course the opposite side of the compass needle is going to be south pole, right? And of course east-west. It's and then now following this convention, as a consequence of this convention, we need to label poles magnetic poles of the Earth, because we just established, we just agreed that the Earth has its own magnetic field, right? So now we can, for example, think of that of the Earth as a basically I don't know, permanent magnet like this, right? This bar, right? You see, rectangular, this rectangle. So basically, like a bar which produces magnetic field, right? Something like this, right? So now, of course, we need to label the poles, right? So now, following this convention, since we know opposite poles attract, if north pole of our compass needle is attracted to this side of the Earth, it means that what? How should we call that side of this permanent magnet of the Earth? Of course, this should be south magnetic pole of the Earth, because again, this north pole of the compass needle attracts, of course, to the opposite side of the opposite side of that permanent magnet, which is the Earth. So as a result, it means that that side of this magnet is the south magnetic pole, right? Okay, so now as a result, this side of the Earth is north magnetic pole. So you see, we have two types of poles: north geographical, south geographical, but magnetic poles are flipped. South, okay, south magnetic, north north magnetic, right? So you see, poles are flipped. We need to remember that. And it's not the whole story. Also, the magnetic poles are slightly offset from the geographical poles, right? Few additional things, a few facts about these magnetic poles. You know what? I like that show, car show, Top Gear, on BBC, right? With Jeremy Clarkson, the old crew, right? Those Three Stooges. Now they're on Amazon. They have the new show, the Grand Tour. But anyway, in one of the episodes when they were still in BBC on Grand Tour in 2006, Jeremy Clarkson and James May, they traveled by car to the North Pole, they claim. So they took that Toyota Helix, I think, or Helix, right? I don't remember how to pronounce it. And yeah, on that car they reached the north. They reached the pole, the North Pole, right? So of course, if they reach the North Pole, so I was curious. Of course, their names must be in the list of people reached the pole. So I went to Wikipedia. So there was a long list of people who reached the pole, and so I started reading about what they actually reached, right? And actually they reached, all those people reached the point where the south magnetic pole was, in 1996. They didn't actually reach the north geographical pole. No, they all reached the point where the south magnetic pole was in 1996. And back then, at that time, that pole was like a few hundred miles away from the one of the Canadian islands. So back then, this south magnetic pole actually used to belong to Canada, right? So they reached that point. So all those people, and actually, North geographical pole, like 1,000 miles away from the south magnetic pole. It's speaking about that offset, right? And by the time when these guys from Top Gear reached this point, the actual place for the south magnetic pole was like again a few hundred miles away. So in 10 years, the south magnetic pole drifted like a few hundred miles. So these magnetic poles, they drift. And that speed is not that small, right? Maybe, who knows, maybe in a million years, these poles, magnetic poles will be flipped, right? Of course, it will change the life on the Earth significantly, right? But again, my point was just to emphasize that, yeah, these magnetic poles drift. And don't trust the shows, right? They can lie a little bit, or not lying. They just don't tell the whole truth, right? But anyway, it was a good show. It is a good show, right? Okay, so now again, remember, two sets of poles, magnetic poles kind of flipped and slightly offset, and that's why on the picture, this magnet, like a permanent magnet, is slightly tilted. Right. Okay, so now the last piece, very important. What about magnetic field direction? And where is it? Here. So if you want to find a direction of the magnetic field, again, we use the compass needle. So position your compass needle, and let's say the north pole of the compass needle points that way. So that's the direction of the magnetic field at that particular point. If compass needle shows this way, so that's the direction of the magnetic field. Compass needle shows this way, so that's the direction of the magnetic field. Right. Okay, so these are three important things, right? So which probe system we're going to use, then convention, and then following this convention, we can label all the poles of any magnets, right? And then direction of the magnetic field. Now, okay, on the next slide, I'm planning to start discussing magnetic field lines. But you know what? This picture doesn't look complete without magnetic field lines. So let me add, without introducing magnetic field lines, let me add them here so that picture would look nice. Okay, so you see magnetic field line, nice curved, right? So of course you see magnetic field line starts at the north pole, north magnetic pole, and sort of ends on the south magnetic pole. And then I can add one more, then more, this, that. Okay, now it looks better. Now it looks much better. So now, after making this picture look nice, we can actually move to the next slide and start introducing magnetic field lines. The idea behind these magnetic field lines is extremely similar to the idea behind electric field lines. Again, magnetic field is invisible, right? So it's good to come up with some lines which can be used to visualize magnetic fields. So again, so we can say quickly, okay, there are magnetic fields stronger, there is a weaker direction of the magnetic field that way, this way. It's very convenient. I don't have to convince you in that. Of course, so now how can we draw those magnetic field lines? An idea is very similar to the idea which we discussed in the world of electricity. Again, so first you map magnetic field. How you can map it? You take your compass needle, right? Position it, for example, at that point. North side of the compass needle gives you direction of the magnetic field. So draw magnetic field vector. Then next, magnetic field vector, then next one, next one, next one, and so on and so forth, right? And then you just connect all those vectors with one solid line. Then take the next point and again start drawing vectors, then again solid line, and so on and so forth, right? Sooner or later you will draw, for example, these are magnetic field lines created, okay, describing magnetic field created by this permanent magnet. You see north pole of the magnet, south pole of the permanent magnet. And you see magnetic field lines, it looks like they start on the north pole and end on the south pole. It looks like. I emphasize on that. Why? Look, you remember in the world of electricity, where did electric field lines started and where did they end? All the time they started on positive charges, basically on positive electric monopoles. Electric field lines started on positive electric monopoles and ended on negative electric monopoles. So you see they started on monopole and ended on a monopole. But now in the world of magnetism, we don't have monopoles. Damn it, right? So where should they start? Where should these magnetic field lines start? Nowhere. They don't start, they don't end. They form closed loops all the time. In the world of magnetism, all magnetic field lines form loops. If you find example where they don't form closed loops, there are two options. Either you found magnetic monopole and you will get Nobel Prize next year, right, immediately, and you will be famous, right? Or you just your picture just not correct, right? Usually the second option is usual the answer. Right. Okay, so anyway, so you see all these magnetic field lines, they form closed loops, and you see through the permanent magnet. You see these dash lines in a permanent magnet. So forming closed loops all the time. But again, it looks like as if magnetic field lines started on the North Pole and ended on the South Pole. It's sort of like this is positive positive point charges in the world of electricity, and this is sort of like a negative point charges in the world of electricity, right? Okay, so then yeah, of course, as I told you, right, so the north side of the compass needle all the time shows the direction of the magnetic field. Then, of course, what about extracting information about the magnetic field from the magnetic field lines? Exactly the same idea, right, like in the world of electricity. Density of lines, density of magnetic field lines give us information about the strength of the magnetic field. So here, magnetic field stronger. Of course, for example, over here, magnetic field is weaker. Then, what about direction of the magnetic field relative to the magnetic field lines? Tangent, right? So, for example, this point, so you see magnetic field line, and in order to get direction of the magnetic field, draw a tangent. Okay, vector tangent to the magnetic field line, right? So lots of similarities with the world of electricity, except for there are no magnetic monopoles. Again, I cannot explain why this is the case. And this is the sort of visualization, not a visualization, right? Sort of demonstration. If you take, for example, an oil or some liquid, right, and you spray some iron filings on the surface of that liquid, and then if you put a permanent magnet in that liquid, so of course all those iron filings, they basically like a small permanent magnets. So they behave like small compass needles. Of course, they're going to orient themselves along the magnetic field lines. And as a result, basically, you see lines which resembles those magnetic field lines, right? Sort of nice demonstration, right? But we have slightly different system sort of set up in the stockroom. But of course, everything is locked up in the department. So I have to just tell you in words. Right? So now, so we introduce some basic ideas, we introduce magnetic field lines, and next, after this, we should start introducing some formulas, because yeah, it's enough to introduce magnetic world on the level of blah blah blah, on the level of words. Now again, we're all science majors, we need to have some expressions. So if we introduce magnetic field, so there must be expression which can be used to calculate magnetic field at this point, that point, and so on. So now it's time to start introducing formulas, expressions. But now the pictures are going to be more complicated in the world of magnetism, and we need to refresh most of this stuff you heard in physics 1, but we need to refresh a few things. So first of all, in this world of magnetism, every problem is going to have three, most of the time, three unique directions. For example, you're going to have three vectors. One is going to point, let's say, up. The other one is going to point, let's say, that way. But there will be all the time the third vector, which is going to point either out towards you or in, away from you. So of course we have to draw all these situations all the time, either on a piece of paper, two-dimensional object, or on a whiteboard, again two-dimensional object. So of course the question, how should we draw these vectors which are out or in on our two-dimensional objects, right? Basically, how should we draw three-dimensional situations on a two-dimensional piece of paper or whiteboard? And we need to introduce vector notation, right? Most of you are familiar with that. For some of you, it will be for the first time, right? Of course, we have different backgrounds. So first of all, so if your vector is into the page, in, or into the board, we're going to use this sign cross, right? Or if, for example, your current, we're going to use that very often, almost every class. Let's say your current is into the page, flowing into the page. We're going to use the symbol, sort of like a circle with a cross. Or here also, if it's a vector, again, very often we're going to draw just a circle and a cross inside. What's the logic behind this cross? It's, imagine, like if you shoot an arrow away from you, because basically arrow is like a vector away from you. So what are you going to see if this arrow flies away from you? You're going to see stabilizers, right? In the simplest possible case, it will be just a cross. So an arrow flying away from you, you're supposed to see the cross. So that's the logic. And I like this picture, this cat, like a world domination for cats, right? Right. So that's if a vector is into the page or into the screen, into the whiteboard. Now, what about opposite situation? If the vector is out of the page, we're going to use either dot or a circle and the dot and the center, in the center, like here, right? So you see, this is a current flowing out of the page. Again, what's the logic? Exactly the same, just flip that arrow, right? So let's say now the arrow flies towards you, right? So what are you going to see? Of course, you're going to see sort of like circle representing the edges of the arrow, and dot represents that sharp tip of that arrow, right? So that's the logic. So from now on, we're going to use these notations almost every class, many times during the class, because again, most of the time we're going to have three-dimensional pictures. Then next, so what about time? Oh, we still have almost 15 minutes. Good. So next, cross product, vector product must be introduced now. Actually, not introduced. You introduced it in physics 1. If you don't remember, I can remind you. Remember when you introduced, for example, the idea of torque, and it was introduced as the cross product between position vector r and the force, basically position vector, which tells you where that force is being applied, r cross f. You used it. Then angular momentum, r cross p. P is the linear momentum, right? So those quantities you introduced using the cross product or vector product. So you at this point you should be familiar, but we need to refresh that, because from now on, almost every equation in the world of magnetism is going to have the cross product. So you must be very, very comfortable with the cross product. If you're not, you're going to struggle a lot, especially on the exam. And you know what? It's funny when we are again at school. It's kind of funny to watch students on the final exam. They will be sitting right, you know, twisting their arms, right, doing some funky moves, right, sometimes moving even their bodies, right. If you don't know, it looks funny, but of course, if you know, they're just trying to apply a right-hand rule properly. Right. So let's refresh that. So first of all, let's compare with the scalar product or dot product, which we already used. In the scalar product, you multiply two vectors. Basically, as inputs, you have two vectors. What do you have as an output? Number, scalar. That's why that product is called the scalar product, right? Because as an output, you have a number, scalar. But in a vector product, you have situation slightly different. Again, you multiply two vectors. Again, as inputs, you have two vectors, A and B. But as an output, you have another vector. In this case, I will call it C. Again, you see, as an output, you have a vector. That's why this product is called the vector product, because as an output, you have a vector. Cross, because we use the symbol cross between these two vectors to show that we are applying the vector product. So now, since as an output you have a vector, let's say it's our vector C, as you see, that's vector C. So, of course, it has magnitude and direction. So we have two steps. First, you can find the magnitude of that vector, and then you can try to find the direction. So in order to find magnitude of that vector, you need to do this. Magnitude of A, magnitude of B, the second vector in the cross product, times sine of the correct angle between them. Again, you remember how we can find the correct angle? You need to position tails of both vectors at the same point, right? And the angle less than 180 degrees is going to be the correct angle. It's the same rule for the cross product, for the vector product, right? You remember we already used that multiple times. So usually finding the absolute value is simple. The troubles are with finding a direction, where you have to apply right hand rule. Again, guys, left-handed guys, sorry, you're being discriminated. You can sue physics, right? But every time, all the rules are about right hand, right? So how does it work? How should we apply right hand rule in order to find the correct direction of the cross product? So first of all, before even you start applying this right hand rule, you need to realize and remember that the cross product C, vector C, all the time must be perpendicular to both of the vectors in the cross product. Okay, you see, we have vector A and B, we multiply them, so they in our cross product. Vector C must be perpendicular to both of them. So it means that it must be perpendicular to the plane where these two vectors lie. All right, so you see, I drew the plane, right? So this vector C must be perpendicular. Every time it must lie on the line perpendicular to this plane. So of course, in general, if before you apply right-hand rule, you can say that the vector C must be either straight down or straight up, right? But after applying right-hand rule, you should be able to tell exact direction. In this case, it should be up. So how you should apply the right-hand rule? There are two approaches, right? So sort of like curling fingers or using three fingers. I usually use this. Right? So how does it work? So first of all, take the first vector in a cross product. The order of these vectors are extremely important. If you flip order, if you change order, the minus will pop up. You see, A cross B equals to minus B cross A. So you have to be careful with the direction of these vectors. Don't change order. Otherwise, direction will be opposite. So you take the first vector in the cross product, in this case A, right? This green vector. And align your hand, right hand. Oh, okay, I usually just use arm, right? In the direction of the first vector in the cross product. So, and align along that direction. So it means that your hand can be positioned like this, like this, like that, like this. Right now, there are no any restrictions. You just fix this direction. Then, second step. Now you need to orient your hand in space, like in such a way so that you can bend your fingers naturally in the direction of the second vector in the cross product. You see, vector b in this cross product, vector b in the cross product is sort of away from the screen towards you. So it means that after aligning my hand along the vector A, I need to orient it in such a way so that I can naturally bend my fingers towards you. Right? If I position my hand, for example, like this, no, I cannot naturally bend my fingers. I need to ask somebody to do that for me, and in that case, that somebody will just break my fingers, right? Oh, dude. So of course, naturally, I cannot do that. Right? Or if I position my hand like this, again, you see, like this. Again, I cannot naturally bend my fingers towards you. No way. Again, if only if I break my fingers. That's not naturally. So there is only one option. I have to orient my hand like this, right? And in this position, I can bend my fingers towards you in the direction of the second vector b. And then my outstretched thumb gives me the correct direction for the cross product. In this case, it's up. And that's what you see in this picture, right? You see, my hand and that hand. So that's how you apply this right hand rule. Again, first align your hand along the first vector A, then orient your hand so that you can naturally bend your fingers in the direction of the second vector in the cross product. And outstretched thumb gives you direction of the cross product. So it's this approach, this method. The second method, it's three fingers. For me, I don't like it because it looks funny, right? That's the only way. I never use three fingers, right? Every time I bend my fingers because it looks like funny. Right, but anyway, so it's completely legitimate. Lots of people use it, right? So nothing wrong with that. So how should you use it? Again, three vectors, so three fingers. This index finger is for vector A. So you need to align it along vector A. Vector B is along this. Sometimes one finger people use. I usually use three fingers, just more convenient, right? And then again, outstretched thumb gives you direction of the correct direction of the cross product. So either way works. Just pick one and start using it. But you must be comfortable. Okay, we're going to practice today, probably till the end of the class, this right hand rule, so that you would feel comfortable, although you applied it in physics 1. And don't wait till the end of the semester, right? So if you, after we practice it here, if you're still not comfortable, come to the office hours. It's not a big deal. It's not a rocket science. It's just simple mechanics, right? Of course, it's easier to practice, face to face, right? Not face to the screen, right? But that's what we have. But anyway, so don't wait till the end. You need to be very comfortable. Otherwise, you will struggle till the end of the semester. From now on, almost every equation is going to have these cross products. All right, so let's see what else. Okay, yeah, I'm not going to start introducing Bio-Savart Law. All right, next class, because we have only, 7 minutes left. So let's practice this right-hand rule. No, not just right-hand rule, finding the direction. Right-hand rule, and I usually call this right-hand rule number 1, because in the next class we will introduce right-hand rule number 2. Right. Again, it's just the way I call them, right? In order to express faster which rule I'm talking about. Right? Okay, so now let me switch to the whiteboard, and I will just pick some random examples to practice a right-hand rule, because yeah, it's very important. Right. And we will practice it till the end of the class. let's assume that we're going to multiply this. So A cross B, and the cross product is C. A cross B. So that's what we want to multiply, apply cross product. And so let me start giving you some configuration of vectors. Let's say that, let's say this is my vector A, and let's say this is my vector, I don't know, B. So what's the direction of the cross product? First of all, before I start applying right-hand rule, again, you must remember that this vector C, the cross product, by definition, again, don't try to find the logic in this rule. It's a just mathematical tool which mathematicians introduced for us physicists so that we can describe some phenomena which we observe in around us, some strange directions. It's like in a torque, right? So r vector can be that way, force can be that way, but the torque is actually up, right? So how can you explain that fact that this torque actually is perpendicular? So mathematicians introduced this tool. So we observed something. Mathematicians can, let's see, what can be done, all right? So yeah, let's use right-hand rule in this way. It seems to be working, right? So don't try to find the logic. You just need to learn how to use it so that we can describe nature around us. All right. So by definition, this vector C must be perpendicular to both of these vectors. Since both of these vectors, A and B, actually I don't like this, that it doesn't have a vector sign on top. It makes me feel uncomfortable immediately. Right. So since both of these vectors lie in the plane of the whiteboard, so vector C must be perpendicular to that. So it can be either out of the board or into the board. So there are two options for the vector C. Now we just need to apply right-hand rule in order to find actually the correct direction. Any other directions would be immediately wrong. If I know at 40 degrees that way, no, that's wrong. Vector C in this case must be perpendicular. All right. Okay, so now let's apply what I told you, right? So first you need to align your hand along vector A. So that way. So that's my, I align it that way. So then, second step, again, it can be like this, like this, like that. So right now, I don't know, just align that way. Then I need to orient my hand in such a way so that I can bend my fingers naturally in the direction, so sort of upward, that direction. So it means that I need to position my hand like this, right, with my palm up. So only in this way, yeah, only in that case, in this case, I can bend my fingers in the direction of B, right? Somewhat up, so above this line, right? So like this. And then my outstretched thumb, you see my thumb, outstretched thumb, is towards you. So it means that the cross product, vector C, is out of the board towards you. So I can, and now I can use that notation where you remember, which we discussed. So out of the board, it means that we need to use what? Dot. Circle with the dot. So this is vector C, out. Okay, so now let's look. You see how it works? Of course, you can use three fingers also in the same, although I don't like that. So this is vector A, index finger. So A. Then vector B that way, so I have to orient my hand like this. So you see these three fingers along B, and this is still along A. And then my thumb, you see, my thumb is towards you. So again, you see, three finger rule gives me exactly the same result, the same direction out. Okay, so now let me give you a slightly different situation. So let's say a vector A and let's say vector I'm just making it up, guys. Sorry. So vector B. So what will be the direction of the cross product? Again, first of all, you need to remember vector C is perpendicular to both of them. So it must lie on this plane, on this line, which is perpendicular to this plane. So it can be either out of the board or into the board, right? So there are only two options, right? So, okay, let's apply right-hand rule properly. First, vector A, first vector in the cross product. First, align your hand along that. Okay, so it should be like this, down. Okay, so let me do it this way. So down, right? So it can be like this, like that. But so next step, so first the correct direction along A. Then B is somewhat up that way, right? So it means that I need to orient my hand like this, right? So with my palm somewhat up, right? So in this case, I can bend my fingers towards B. You see, my fingers is somewhat in that direction. So like B, right? And so my outstretched thumb, you see my thumb, is into the board. So in this case, vector C is into the board. Into the board, it means according to our convention, we need to use cross, right? So that's how it works in this plane, when both vectors are in this plane, But what if I give you this example? What if I have vector A into the board? No, it's out of the board. I'm just making it up completely on the fly, right? And let's say vector B is down. So effectively, which situation do we have here? A is out of the board, so towards you. So it means that vector is out, right? And vector B is down. So effectively, we have this situation, right? Turned by 90 degrees, right? So now the same rule. But now, of course, you have to sometimes move your body to make it more convenient for you to twist your arms. So A, first, align your hand along A. So it means that towards you, I have to align my hand like this. Right, so it's towards you, first vector. Then you need to orient your hand in such a way so that you can bend naturally your fingers along the vector B. B is straight down. So if I position my hand like this, no way, right? Yeah, I have to ask somebody to break my fingers in that case, right? No, it's not natural. This way also not natural. Although I know, like in Southeast Asia, right, in their traditional dancing, they can really bend their fingers down, but that's not natural. not in these countries, right? So naturally, it means that I have to position my hand like this, all right? And now I can naturally bend my fingers down in the direction of the second vector, B. And you see my thumb now is that way. That's the correct direction for the vector C, right? So that's the direction of vector C, that way. Right. And again, as I told you already several times, you remember vector C cross product must be perpendicular to both of these vectors. Vector A and B, they form this plane, right? So vector C can be this way or that way, must be perpendicular. So but we apply right-hand rule and we found that this is correct direction for vector C.